right, I think we might begin. Unlocked, the upcoming talk takes this year's Congress motto quite literally. Based on the need for a wireless door lock solution, members of the Mainframe Hackerspace in Oldenburg came up with an unusual form of lockpicking. No wrenches or hooks needed. That sounds interesting to me. So if you want to know the ingredients for their lockpicking recipe, please stay with us and listen to what our speaker, Sebastian, aka SRE, has to say. SRE is not only co-founder of the Mainframe Hackerspace, but also active in the third crew. So let's give him an extra warm round of applause and welcome to the stage, SRE.
Thank you. So before coming to the log that we will have a look at most of this talk, let me present you with our current solution, which is the CFA 1000. It's quite common in a few hackerspaces for a few years because you can remove the radio part from it and wire it to have a safe system, and also schematics are more or less public. So we are using this for some years to lock our doors in a more or less secure way because no wireless things are involved. But it has some issues. First of all, the wiring is a little bit ugly, so we tried to find a different solution for the future. And the future, well, was actually in the past by now because we got a really big CNC mill that we put in the basement, so we needed a new solution. And the obvious choice was to have a look at the successor product, which is supposed to use the advanced encryption standard. So we used the, well, maker solution, wired some things to the remote control, added a Raspberry Pi, and pressed the buttons so that the door can be locked and unlocked. Knowing that the solution might not be that secure, but it's not so easy to steal a 2-ton CNC mill. But once we have this solution set up, I got curious and had a look at what's going on the radio frequency. Is the protocol actually secure? So I set up an SDR and had a look and got this. So it's a quite clear picture because in the basement there's not lots of radio traffic going on. So as you can see, it's quite easy to find the frequency where the remote control is operating at, and also it's, if you have some ham radio background, you can see that it's using some kind of frequency modulation with the 100 kilohertz deviation. So next I started to set up a GNU radio project to try to decode this, and this is what I came up with. So there's a input block which gets the data from the software-defined radio, then puts it again into a waterfall sync, which is basically what we just saw. Then additionally, I added a block to demodulate the signal and then put it into a sync that is just showing us the demodulated data. And after running this, I got this nice data. So it's already quite easy to see, oh, looks like ones and zeros, but we still need to decode it. What this data is already telling us is the baud rate, if we expect that these are ones and zeros, which is quite likely, because if you're sending data over radio, you somehow need to refine the clock, so usually a transmission starts with a 1-0 pattern. So looking at this, we can count the numbers of bits that are sent within a specific time and then recover the baud rate from this and use that to improve our decoding pipeline, which is what I did. There's a nice blog available from GNU Radio. The Muller and Muller, the ham radio people in the room will probably know this. So it's basically trying to recover where a bit is starting, and then afterwards it's converted into binary so that we no longer have an analog signal but nice bytes. So every bit will become a byte. What is still missing, though, is the information where a byte is starting, and to figure that out, it's needed to have a look at the stream that is generated, so we get lots of ones and zeros and try to find patterns. I did this next, and I don't want to bore you with all the data, so I will just give you the result. So this kind of header is what could be found lots of times in the data, and then there's a fixed amount of bits following afterwards. And with that information, we can yet again improve the decoding pipeline and create nice packets, which is what you can see here. So this sync word is basically the pattern that I just showed you. And then there's the fixed packet length. And the output is a nice packet that is sent to UDP that can be post-processed. So the next step is having a look at the data. And for that, I have a really simple Python script for you, which just receives the data that has just been provided by GNU Radio and prints it on the terminal. And after all of this, I got this nice table. So every line is a new packet, and you can see they are looking all quite similar. The only differences are in column 8, 10, and 11. And often, if we're doing data transmission, we end it with some kind of checksum. So if one column is different, of course, the checksum would also be different. So that's what I expect. And the other interesting part is that in column 8, it looks a little bit like a counter, but then it swaps over in some line over here. And also the data looks a little bit like it might be scrambled, which is something you often do when doing radio transmissions in order to avoid having long periods of ones or zeros, which are hard to decode. So the information missing is what kind of checksum is being used and what kind of data scrambling is being used, which probably could be recovered by, trying different things. But what I did was having a look at the hardware and having a look at what it might provide. So this is the remote control from the door lock system, and it actually has 2 chips, which should be easy to see on the picture. And they haven't been scrubbed, so it's still possible to read what is written onto them and to identify them. And one of them is a microcontroller, which has the buttons and the LEDs connected to it. And the other one is a chip, which is a radio transmission chip. And this specific chip, it has a public documentation. And if you look into it, you can see, it supports automatic generation of a checksum and also automatic checking of it. And it has 2 optional encodings. One of which is a Manchester encoding, and one is a linear feedback shift register polynomial. So both would be options that are quite likely. So I first of all had to look at Manchester encoding. And in Manchester encoding, there can't be more than 2 sequential identical bits. So 0, 0, 0 or 1, 1, 1 wouldn't be possible in this encoding. But the received packets, they do have this kind of sequence. And I saw quite a few of those sequences, so it's unlikely that I received data incorrectly. So I assumed that this is not Manchester encoding, and then tried the polynomials thing. So I updated the Python script a little bit and added those 2 algorithms, the CRC and the encoding thing, and got this nice new table. So you can see the CRC checksums, they are all fine. So it's highly likely that this is being used. Also now lots of zeros are being transmitted, which looks kind of sensible. And our counter changed a little bit. It's now a decreasing counter, starting at 99 and then counting down, and there are no longer any jumps. And also as a side effect, we now have 16 bytes of actual data, and the vendor officially says that this product is using AES 128 bits. Now our packets are exactly 128 bits, so that seems quite likely. So in the next step, I had to look at the following packets. As you might have guessed, the interesting part might start once the counter reaches 0. So the first messages that we saw, there are 100 of them, and I will name them message A here. Then there's 2 different messages that are following, a message B, which is sent back from the door, and a final message C in some cases. So let's first of all have a look at the message A. As I mentioned, that's sent 100 times, and by using different remote controls, it's possible to see that there are 6 bytes that are using, well, some kind of address for the remote control. I myself call it a MAC address because it's quite similar to it. And then there's a byte which tells the door what the remote control wants to do, if it wants to lock or if it wants to unlock. And then the counter that we already saw, and all the remaining data is 0. Next, the door answers, and it sends this message B, which looks very similar. It effectively sends back the address, doing some bit magic on it, sends back the command, and then the zeros are filled with some data. At the end, there's a status, so even without any encryption being done, the door already tells us, hey, I'm unlocked. So if you ever want to know if your neighbor's door is locked, well, you can just ask it. The other bit that is in there is some kind of challenge. You will know what I mean with this by having a look at the next message, which is message C. That one is only sent if the remote control wants to lock or unlock the door, because if it only wants to know the status, it already got told. And if it wants to, well, lock, then there's one more packet, and that seems to be encrypted, like the data is pretty arbitrary. But if I use like a fake CFA 3000, like if I use a software-defined radio to, well, basically appear like a door lock, and then send the same challenge again, I will get the same message again. And that's why I say that those bytes contain a challenge, because if those bytes change, then the message C also changes. So what does this mean? If we have a look again at the protocol being used, we effectively can generate the first 2 packets, and what is missing is the last packet. So if we can somehow break it, it means we can open all the doors. So I was wondering, how hard could it be? But before having a closer look, I also looked at how does the pairing work. And that was quite interesting, because it's really simple. You tell the door lock, please learn a new remote control. Then you press any button on the remote control, it sends out the 100 packets, and then you're done. So if you follow the talk, you will notice the only thing that the door gets told is if it should lock or unlock, which does not make sense for learning a new remote control, and the MAC address of the remote control, but there's no key exchange. So the key must already be there, and it must be the same on all the locks. Right, so can I get the key? Let's have another look at the microcontroller. So the microcontroller being used is a quite small PIC. It only has 1 memory block. So if you remember the talks from previous congresses, there is an attack that you can use on PIC microcontrollers where you're erasing the first block and then flash some code into the first block to read out the second block. But that's not possible on this one because it only has 1 memory block. That leaves us with, well, trying to do power or voltage glitching, which is quite hard. Maybe use a Chinese service. They're offering to read out the chips for around $5,000, which, well, I didn't want it to do. Then there's the option of using a scanning electron microscope, which I, well, didn't really consider until a member of my hackerspace told me, well, where's the problem I have? I can get us one. It's on eBay. So, well, we bought a scanning electron microscope. So, it was marked as broken, so we thought, let's ship it to us. But the previous owner, they told us, well, it's better if you get it from us, then we can tell you how it works and give you some ideas how it could be fixed. So we went over there, and it was, well, not working perfectly, but more or less working. And we got it running, we got some pictures. These are not from the PIC, they are from some parts from the scanning electron microscope that were broken. But the problem with this device is it's quite old. It needs lots of maintenance, like maybe running it for 2 hours, then something breaks and needs to be fixed. And also, so far, we failed to actually open the PIC. You have to deal with like strong acids and to etch it open, and yeah, I'm not feeling comfortable with this, but we are still trying to do this. But I'm here, so we found another solution. During COVID, the batteries and the door lock actually went empty, so I had to replace them and thought maybe have a look at what is inside of the door lock. And I found this. So the door lock has a lot bigger PIC, which has multiple memory banks. So I thought, great. That means I can probably do the same attack that has been shown before. So I prepared a small breakout board for the PIC to do some testing, and also wired up the door lock to a Raspberry Pi, which can be used as a programmer, and to get the serial. Then dumped the fuses and got this nice result. So I can see it's like all code protected, so over the programming interface I cannot just read the code, which is kind of expected. But I also saw, wait, in the first block one of the fuses is missing. So that was interesting, and I tried to repeat the attack shown before, which works a little bit like this. So you erase the first memory block of the device, and then you can write your own code into it, leaving the other blocks intact. And the code written to it looks more or less like this. So there is a serial setup, so that I can dump data over serial. Then this address, the 1000 in hexadecimal, and the 2000, that's the first block. And I just loop over it, read the bytes, and print it out. And then I have the data block. Unfortunately, that only works for this block and not for the others, because Microchip introduced a new protection feature. That's the TBR that you can read over here. That means they are table read protected. And this protection is interesting because it does not fully block the table read. What this fuse bit does is it does not allow to read data from a different block. So if the table read instruction is in block 0, but the data that should be read is in block 2 and that has the table read protection, it will just return a fixed value, let's say 0. But if the table read instruction is also in block 2, then it will return the correct data. The idea behind that is you cannot add a table read instruction in block 2 without erasing it, and if you erase it, you also erase the fuse bits. But knowing this, I was wondering, maybe there's already a table read instruction somewhere in there. And as you can see in the example assembly that I show here, the pointer that points to what address should be read, it's not part of the instruction itself. So if I can prepare this pointer register and then jump to the table read instruction, it will read something else. So I prepared a nice flowchart for you. My plan was, first of all, ask for the address that should be read. Then initialize the register where the result is being stored. Then set up the table read pointer. Enable the interrupts. And then the interesting part happens. I program a timer that I want an interrupt in 2 instructions. The first instruction is the falling jump, which jumps to the instruction where I hope that the table read instruction is. And the second instruction will be the instruction that should be, hopefully, the table read instruction. Now, what can happen is, first of all, maybe the interrupt does not trigger. For example, if I jump to an instruction that disables interrupts, well, the interrupt will never be there. Then the second option is there will be an interrupt. And if there's an interrupt, I have again 2 options. Either the register where the table read instruction stores its results, it's still 0 as I initialized it, or it changed. Now if it's still 0, I know 100% that this is not a table read instruction, because the address that I try to read is the same address where I jump to, so it must be the bit sequence for the table read instruction. So that was my plan, and I tried it with the development board that I did build, and everything worked fine. So then I tried it on the real device, and unfortunately there was not a single table read instruction. So the plan failed. But the same mechanism can be used to find other instructions. So I modified the pipeline a little bit so that I'm no longer looking for table read instructions, but instead try to see how the program counter changes. So effectively, I'm looking at the stack. So if you read TOS, that's top of stack, I initialize it to that, just a specific value that I will be able to recognize. Then do the same thing again, enable the interrupts, set up the timer, jump to the address, hope that an interrupt triggers, and if it triggers, I have a look at the stack. If the stack is the jump address plus 2 bytes, it means one instruction has been done, let's say an add or a knob or whatever, and now the program counter of the normal code is one instruction later. The reason for that is that the triggering interrupt, it takes the current code position and puts it on the stack, so that once the interrupt returns, it will be back to where the code was currently running. If instead the top of stack shows me 0xDat, that's the value we initially put there, it means that the instruction that I just executed is a return, because the return looks at the top of the stack and puts it to the current program counter. So great, we just recovered an instruction. I can also have a look at what is at the stack -1, and if that is the jump address +2 or +4, then the code actually did a call into some other function. And last but not least, there might be the option that the top of stack is not dead, but it's also not the jump address +2, and in that case, I just found a goto. So this can be used to figure out more or less every function and every jump, and also where the functions return. Which is not all the instructions, but it's quite interesting to get a better understanding of how the code is being structured. But the same mechanism can also be used to figure out any other instruction. So same concept again, initializing the device to a specific state, and then do the interrupt trick, jump somewhere, wait for the interrupt, and then dump the whole device state. Let's say, for example, I try to find an instruction and I'm wondering if it's doing an add. It needs to store the result somewhere and it needs to get the initial values from somewhere. So if I initialize the memory to 0000, and afterwards somewhere there's a different value, obviously that has been changed by this instruction. So let's take an example. This was the output from the previous code. So we can see one of the registers changed. First it changed from 0 to FF. Then in the second one, where the memory was initialized differently, it changed from FF to FE. Then it changed from 42 to 41. Then it changed from 11 to 10. So, well, most likely this will decrement the register. This looks quite simple, but in some cases it's a lot harder. I have a second example. This is an instruction that is located at address 1337DA, which is made up, by the way. And this register changed from 0 to DA in all cases. So it might be that this instruction is just writing a fixed value of DA, but it might also be involved to the instruction somehow, because the lowest byte of the instruction address is exactly the same. And so the assumption that I had is that this might write the working register, because the working register contains the lowest byte of the instruction position as a side effect of how the jump is working. So I was wondering if I can somehow modify it and figured out I can jump a little bit off. So the instructions are 16 bits, which means effectively they are only even instructions. But you can jump to an uneven position and it will still execute the instruction, just with a different working register. And I can see, well, now the register changed to dB. So it's very likely that this instruction is actually writing the working register into the specific register. So great, I have a way to recover instructions. It's, well, a little bit of work, but it should be possible to get everything out without the scanning electron microscope. Except for the block 0, because, well, that's where the interrupt handler is. So I might be lucky if the interrupt handler from the original block jumps into some other block. And then, of course, I get the code running again. If that's not the case, I need to find a way to do all of this without interrupts. Well, I didn't. But of course, it's still possible to find returns, because jumping to it means the code will come back. And we can still enable the timer and figure out how many instructions have been executed. And yeah, one more thing that I figured out while doing this, I had quite some issues initially that the device resets all the time, because, well, the firmware enabled the watchdog. And if you do a big, long knob slide, like you usually do for doing this attack, that's too long, so the watchdog will reset the device. So I have a nice tip: don't use knob slides, use call slides. That also has the nice side effect that you know where exactly block 0 jumped to, which is, well, always nice to know. So after doing all of this, I found this sequence. And I was like, okay, that looks interesting. So this is directly after each other. So it's a return, and the next instruction is also a return, and the next instruction is also a return. So it looks a little bit like a lookup table, and some of you might know this byte sequence. If you don't, you can just put it into your search engine, and it will come up with this, which I took from Wikipedia. It's the S-box from the Advanced Encryption Standard, which means I just found the lookup table for it. And as you remember, I already uncovered all the function entry points and exit points. And what I did with this information is I created a graph. And now I know where in this graph the S-box is. And of course, anything that uses the S-box is related to the Advanced Encryption Standard. And I also know how many instructions it's using. So now I can try to, well, investigate specific functions instead of having to debug and reverse engineer the whole firmware. So there's a nice webcomic that I remembered from university. You can find the URL here. It will explain how to implement AES, but it starts with this nice food shooting prevention agreement, which tells you, please don't do a custom implementation of the Advanced Encryption Standard, because you will probably not be able to implement it without having lots of side channel attacks that will be possible on this algorithm. So yeah, it's usually you don't do it, and also programmers are lazy, so they want to use a, well, ready-to-use implementation. So I had to look what kind of implementations exist for the PIC. And Microchip is nice. They are providing 2 application nodes, one for the PIC18 and one for the PIC16 series, which implement the WinJail algorithm, so the Advanced Encryption Standard. So I had to look at the first one. The obvious choice is the PIC18, and that, of course, has an S-box inside, but it's using the table read instruction, which I already noticed is not being used by the door lock. So probably they're not using the algorithm from that. And afterwards, I had a hinge and also looked at the PIC16 implementation, because that's used by the remote control, as you might remember. And that one had an IES box using lots of returns, like exactly the sequence that I found. with that information, I tried to match the functions that they provided. So it's nice because it's all in assembly, so it actually fits exactly. So I could update my graph and had function names for all the functions related to the advanced encryption standard. So now I know exactly which instruction I need to figure out to understand where the key is being stored. And I did this and extracted all the necessary information, which means we can update the flowchart from before, because now I can also generate an encrypted response. So I updated my Python script from the beginning and renamed it a little bit. It's now named like the remote control, and it's now bidirectional. And I can, well, provide the MAC address and also the instruction, like if the door should be locked or unlocked. And then it will send 100 packets with the decreasing counter, wait for the challenge, and send a nice encrypted response. And what you can see here, well, actually works on a real device, except that you probably won't find a remote control that has the MAC address bad-coded AES. So all of this more or less happened at the last remote congress. So a few days afterwards, I actually had full access to the door and asked our nice people from CCC, the disclosure people, if they had any prior experience with the vendor. I got a nice link we actually had. And I got told, well, it's probably sensible to send this to the CERT, which I did. And then it took quite a while. The idea was that hopefully they can fix it. But the response was, well, this product is more or less end of life, and we don't think we can fix the bug. We consider it unfixable, which kind of makes sense. Like there's no user interface to update the firmware, so they would have to take back all the logs and update the firmware. And also, if they update the firmware from the logs so that they are secure, they also need to update the firmware from all the remote controls, and they will no longer be compatible. So here, it's a bit hard to fix. So they got told, yeah, please provide the security information to your customers that this device is no longer secure. Then a long time, nothing happened. Then we had the camp, and during camp I got a nice message from the CERT band, and they told me, well, we plan to take care of it ourselves now, which they did a few days later, with a nice big warning that this device shouldn't be used at all anymore. But of course, it's not nice to have a device that is broken and doesn't work, and so I tried to find a way around it. And well, we now have a custom implementation of a remote control for our door lock. And I asked the vendor if they would be willing to open the firmware so that fixed one could be written easily. Unfortunately, they denied. We do have some workarounds for our implementation, but I don't intend to publish them because that would mean that everyone can unlock everyone's doors that have not been updated, which wouldn't be too nice. So we're sorry about that. And actually, that's it, and I'm available for questions.
Well, thanks, SRE, for this talk. We do have plenty of time for questions, and yes, please, we do have 4 mics here in the saal, in the hall. If you have any questions now, don't shy away from them. Come on, I know there's something in you. Otherwise, I would ask the Signal Angels. Maybe we already have some questions from the internet. Not right now. All right. We have to unlock the questions. Sorry. Yes, please go to the, over there. Oh, nice, thank you. Mic 4, please.
So we've seen that the BSI has issued some warning. Did ABUS also issue some warning, or how did they react?
After the BSI did a warning for the product, they updated their website because they got lots of customers complaining and asking questions about this.
So what was their take on it? So sorry, it's broken. It's your fault now.
So the take that ABUS did was they told, well, it's quite hard to do this, and you need to have a very criminal mind to open a door in this way.
Great comment. All right. Looking at Signal Angel, all right. So would you be free for questions and drinks and congratulations and everything else after the talk?
Yes.
Okay, so I think then if there aren't any questions left, last chance. Anybody? No? Okay, then we wish you all the best for tonight, and thanks again. There's a question? No, come back, please. We do have time. Okay, Mike.
Hello. I just want to make sure the AIC key is hard code inside the firmware. Is it?
Yes, so there's not a single one, it's a little bit more complex. They have some kind of rolling key scheme inside, but yes, it's fixed in the firmware.
Okay, thank you.
And another one. We unlocked the questions now. Very good.
Well, first of all, thank you very much for your talk. Did you ever get the electron microscope to work?
Yeah, so as I said, we got it working. We have it at our Hackerspace, so if you want to take a look, come by and have a close look. The part that is still not working is we didn't manage to open the chip.
Okay, thank you very much.
That's good storytelling, I would say. So now we have a question, I believe, from Signal.
The internet is asking, did you do any experimentation with glitching the PIC? Or if not, why not?
I did not, because I found the alternative of doing it in software, which is a lot more stable and a lot easier to do.
Short answer to a short question. Yeah, guys, if you want to ask, or everyone around here, just come, don't shy out of talking into a microphone. I will give you a few more seconds, maybe. The mics are here in the lanes and the different ones. So, another question? Yeah? Okay. Then I will finally close this session. Okay, last chance. I don't see anyone. Okay. So thanks, SAE. Please visit him afterwards. Thank you for your talk.